Bismillahirrahmanirrahim. I'm your course instructor Muhammad Kashif, and the course name is Design and Analysis of Algorithm. Students, today we are going to discuss a new topic, that is a delete function in a heap sort algorithm. And as you know, we have already covered in our previous lecture, we've talked about min heap and max heap, in which you have observed that in a min heap our parent node should be smaller than its all descendants, and in a max heap the parent node should be greater than its all descendants on each level. So in every level we try to make a root node that should be greater in a max case, or that should be a smaller in a min heap situation. So these are the conditions that we have to met in max or min heap algorithms. And second most important condition that we satisfy while we are making a heap, or the tree, that is a complete tree. That tree should be a complete. That means we have to follow a pre-order in which parent node should be explored first, then we move on the left child, and then we move on to the right child. So this is the precondition that we satisfy in each situation while we are making max heap or min heap. In today's lecture, what you are going to learn, you will learn how to delete the nodes in max heap or a min heap, and how to get the sorted data. Obviously, our purpose to study this particular algorithm to sort the data, so that we can get the data in minimum time complexity, and or we can fetch the data in a minimum execution time. So for this particular algorithm, we have to we should know the concept of deleting the nodes, and for deleting there are some rules that we have to obey or follow in this particular algorithm. So first of all, we have to take an example, and as you can see on your screen, we have some data elements, and we have to observe what type of heap is it. And as you can see, we have min heap. Basically, if you observe deeply the problem, there are some nodes, and on each level the parent node is smaller than its descendants. If we talk about this level, 75 is smaller than 100 and 150. And if we move down, we can see 100 is smaller than 200 and 250. 150 is smaller than 165 and 185. And if we talk about this level, you can see uh, 200 is smaller than 300, and 200 is smaller than 350, and 250 is smaller than 260 and 265. Uh, and obviously, we are discussing about the delete function. Delete in min heap. All right. So min heap means we have a tree, we have a problem in which the parent node should be smaller than all its descendants on each level. Right. So there are two conditions that we have satisfy while we are deleting in any problem, while whether is it a min heap or a max heap. First condition is delete the root node, and second condition is replace the root node with its last child. Last child. All right. Uh, when we need to identify the last child or last node of a tree, that doesn't mean we have 85, because most of the students do a mistake. They got 185 as a last node, because last means by using the property of a complete tree, and that is our parent left and right, and by traversing in pre-order we move on the last node, that is 265. So 265 is basically the last node of a given heap. So as we discussed that as we study, or you can say I told you that there are two conditions that we have to satisfy while we are deleting. First one is delete the root node, and if we delete the root node, what data element should take place of this root node. That means if we are going to delete our 75, that means we are going to remove 75 in a given heap, and obviously the last element is 265, right? So where this 75 will take place, so we have to assume a separate array. We have to assume a separate space in our computer where we want to place the deleted data items, right? So how we can use these deleted data items, you will observe in the last of the lecture. The array would be in an order, and that order would be observed accordingly, right? So first of all, we deleted 75, and we place this 75 into another array, right? So now what we are going to do, we are going to, as the definition, replace the root node with its last child. So last child is basically 265. So 265 will go up, right? So 75, as you can see, is deleted from the heap, and 265 will take place of 75. So if we rearrange the heap, we can see 265 is deleted, and 75 is basically removed from the heap, and 75 will be placed over here, that is a separate array. And now we are going to place 265 over here, right? So now the next thing that we have to check whether it is satisfying the property of a min heap or not. So obviously it's not, because min heap says the root node should be smaller than all its descendants. So if we check our first level, it's not satisfying the property of a min heap. 265 is not smaller than 100 and 150. So what we are going to do now, we are going to call a min heap function that we have, that definitely we will write in our algorithm, and we will call a min function. And what that function will do, that will do a check whether it's left child or a right with a right child. So 265 will compare whether it's left children or with the right children. So 265 is not smaller than 100, so 265 will go down, and 100 will go up, right? So 100 will move here, and 265 will move down. Now 100 becomes a root node that is already smaller than 150, right? So what we are going to do here, we are going to again check level by level, right? Because obviously by doing swapping, our tree has been changed. Now as you can see, 265 uh, take place of 100, and 265 becomes a root node of 200 and 250. So now we are going to compare 265 with 200 and with 250. So 265 is not greater than not smaller than 200. Now what we are going to do, we are going to again do perform swapping. So 200 will take place, and 265 will come here, right? So now we have checked this level, but at this level 150 is already smaller than 165, and 150 is smaller than 185, right? So what we are going to do now, again we are going to check this level. So at this level, 265 is smaller than 300, yes. 265 is smaller than 350, yes. At this level, 250 is smaller than 260. So on each level, we can see 100 is smaller than 200, 100 is smaller than 150, 200 is smaller than 265, 200 is smaller than 250, 150 is smaller than 165, 150 is smaller than 185. So on each level, we can see our heap is basically following the property of a min heap, and that is basically the root node should be smaller than its all descendants. So the new heap would be like this, and as you can see, I will draw a new heap, and that would be like 100 becomes a root node, right? 100 would be like this if I rewrite it, because it 100 become a root node. So 100 becomes the root node, and its left children would be 200, and our right children would be 150. And on our left 200, we have 265, and on a right of 200 we have 250, right? On a left of 150 we have 165, and on a right of 150 we have 185, right? And on a 265 we have a data element on a left, that is 300, and on a right of 265 we have 350. All right, and on a left of 250 we have 260. So now this heap is satisfying the property of a min heap. And what we have done before, we remove the root node and place that data element into the array. And the last element will take place the root node. So what we are going to do, we are going to delete our 100. So 100 would be deleted from the heap, and 100 would will be placed over here. 100 will be placed over here, and 265 will take place of 100. So 260 will be placed over here, right? So that means our heap would be like this, right? 100 is moved to the array, and 260 will come up, right? So new heap would be like this. So now again we will check the property of our min heap, and min heap says the root node should be smaller, but 260 is not smaller than 200. 260 is not smaller than 150. What we are going to do, we are going to perform swapping. So 260 will move down, so 200 will come up, and 260 will move down. Now 200 will be checked with its right descendant, and that says 150 is smaller than 200. So basically 150 will come up, and 200 will go down. So the new tree would be like this: 150, 150 has two children, and left children would be 260, and right child would be 200. And on a left of 260 we have 265, and right of 260 we have 250, and left of 200 we have 165, and right of 200 we have 185, and the left of 265 we have 360, and on right we have 350. All right, now we will check again level by level. 150 is smaller than 260, 150 is smaller than 200. At this level 260 is smaller than 265, but 260 is not smaller than 250. So 260 will go down, and 250 will take place of 160 260, right? So this will be crossed, this will be crossed, and at this level 200 is greater than 165. So 165 will take place of 200, and 200 will take place of 165. 165 is smaller than 185, so we don't perform swapping over here. Now at this level 265 is smaller than 360, 265 is smaller than 350. Now the new tree would be like this, and we have to redraw it. And after redraw the heap, we have a situation, and in which 150 becomes a parent node, and on a left of 150 we have 250, on a right of 150 we have 165, and on a left of 250 we have 265, on a right of 250 we have 260, on a left of 165 we have 200, and on a right of 165 we have 185, on a left of 265 we have 360, and on a right of 265 we have 350. All right, so this is the situation we've got after doing swappings and the iterations. So now what we have to do, we have to check whether we are satisfying the property of heap sort or not, min heap or not. 150 is smaller, 250, 165, 250 is smaller both the child, 165 is smaller than both the child, 265 is smaller than. So what we are going to do, we are going to delete 150. So when we delete 150, we will place this 150 into an array, and that array 150 would be placed over here, and the last child, obviously second condition was to replace our last node with our root node. So 350 will take place of 150. So now we are going to delete 350 from the heap, and that will take place of 150. So now our new tree would be like this. 350 becomes a root node, right? So when 350 becomes a root node, that means we need to again check level by level whether we are satisfying the property of our min heap or not. And obviously we are not satisfying the property of our min heap, because 350 is not less than 250 or 165. So 250 will go up, and 350 will move down. Now 250 will compare with its right child, so 165 will go up, and 250 will move down, right? So now you can see on each level our tree has been changed now. So 250 will be crossed. Now 350 will be checked with its left child. So 350 is greater than 265. So 350 will move down, and 265 will move up, and 350 would be placed over here, and 265 is crossed. Now 265 will be checked with 260. So 260 is less than 265. So 260 will take place, and 265 will exchange with 260. Now at this level, 200 is basically less than 250. So 200 will come up, and now we need to rewrite it. 200 will go up, and 250 will go down. Now we need to cross the 200, and now 200 will compare with 185. So 185 is smaller than 200. So 185 will go up. Need to a little area. Uh, 185 will go up, and 200 will go down. So 200 will come here, and 185 will go up, right? So at this level, 350 is already smaller than 360. So now we need to rewrite our tree because our tree has been changed, our heap has been basically changed. So now let's redraw it and check whether we are satisfying the properties or not. So 165 is basically the root node. 165 is a root node, and on the left of 165 we have 260, and on the right of 165 we have 185, right? 185. And on a left of 260 we have 350, and on a right of 260 we have 265. All right, and on a left of 150 we have 250, and on a right of 185 we have 200. All right, and now we are going to place the last element, that is 360, and that exists on a left of 350. Now you can see on each level the root node is smaller than its all descendants, right? So what we are going to do, we are going to delete 165 and replace with the last element. The last element is 360, and we are going to place 165 over here. When we place 165 in a new array that we have defined, that we have created, so the last, there is a space available where we can place our last element, and that would be 360, right? So 360 will take place of, as a root node. 360 becomes a root node. Now we again will delete these nodes, or because we have to write over here, so we can delete this heap. Now what we are going to do, we are going to again check level by level. 360 is smaller than 260. No, it's not, because it's not satisfying the property of our main heap. So what we are going to do, we are going to perform swapping. So 260 will go up and 360 will go down. Right now 260 will compare with 185, so 185 will go up and 260 will go down, right? So at this level we will check 360 is greater than 350, so we will perform again swapping. So 350 will go up, and 360 will go down. And now we will compare 350 with 265. So 350 becomes a child, and 265 becomes a parent node. So 350 would be crossed. Now at this level 260 is greater than 250, so 250 will move up, and 260 becomes a child node. And now 250 will compare with 200, so 200 will move up, and 250 becomes a child node. Right, so the new tree would be like this: 185, left would be 265, right would be 200, and on a left of 265 we have 360, on a right we have 350, and on a left of 200 we have 260, and on a right of 200 we have 250. Right, so this is actually a tree we have got after traversing our problem. Now we need to raise And